In this video, we're going to focus on something called linear regression or line of best fit. But before we do that, let's tackle these 4 warm-up problems that we have for you today. So take a second and see if you can try those 4. Okay, so in number 1, we have 2 lines here. Both are y equals a particular number, and I'll just do a rough sketch here real quick. Here, y equals 7 will be at 7. It'll be a horizontal line up here, parallel to the x-axis. And then, of course, y equals -4 will be down here, same thing, parallel to the x-axis, down here at -4. If it's x equals a number, then we'll have a vertical line. So if it was x equals -4, then it would be left 4, and it'd be a vertical line, where every point on that line has an x value of -4. That's how I kind of like to think about it. Whereas this one up here, y equals 7, every point on this horizontal line here, every point has a y value of 7. And so it's just a plotting of all of those points. Number 2, given g of x is equal to 8/7 x plus 3, find f of 1, 7, 14, and 21. So we're substituting those numbers in for x each time. So when we substitute in 1, we're going to get, this should say f here. F of 1 equals 8/7 times 1 plus 3. 1 times 8/7 is 8/7, plus 3 would be 3 plus an additional 8/7. So what I want you to think about this is the y-intercept, right? 3. Okay, so if I substitute in 1, that means I'm thinking about what the y value is when x is 1. So if I go over 1 from the y-axis over to 1, I'm going to go up 8/7 from there. Okay, so I start at 3, then I go right 1, up 8/7. So for every increase of 1, I'm going to go up 8/7. That's one way to think about it. But if I do f of 7, that's going to be 8/7 times 7 plus 3. Well, the 7's reduced to 1, leaving us with just 8. So if I go over 7, so again, I'm starting at the y-intercept 0, 3, and I go over 7, then I go up 8, because when I'm substituting 7, I get an additional 8 out. So I could go over 1, up 8/7, or I could go over 7, up 8. Or, how about f of 14? You probably imagine what's going to happen here. 8/7 times 14 plus 3. 14 divided by 7 is 2. So that's reduced to 2. And then 2 times 8 is 16. So it's going to be 16 plus the 3. So I could go over 1, up 8/7. I could go over 7, up 8. I could go over 14, up 16. Or I could go over 21, up 24, if you were able to do that as well. So it just kind of shows you that this idea of slope and how we can think about the different ways that we can do the slope. We can go over 1 or we can go over 7. Multiples of the denominator are the best when we have a fraction as the slope. Number 3, multiply 1/16 times 4/7. Well, we can actually simplify any numerator with any denominator if there's multiplication in between here. So 4 and 16, that's 4 goes into 4 once, 4 goes into 16 4 times. So we're left with 1 times 1 across the top is 1, and then 4 times 7 across the denominator is 28, so 128. Number 4, given y equals -6x plus 1, explain what -6 means. So going back to number 2 in our warm-up, it's talking about the slope, right? For every increase of 1 in x, we go down 6 in the y. That's the basic definition of slope. As you can think about it, for every increase of 1 in x, we go up or down that many. Just like we did up here, right? For every increase of 1 in x, we went up that many. Or in this case, down 6. All right, so let's go ahead and move on to our topic for today, which is all about what's called linear regression or line of best fit. So it says create linear functions to represent the relationship between two quantities. And we're going to use technology to do that. I'm going to show you Desmos, and then I'm going to show you how to do it in your calculator as well. And then secondly, interpret the slope and y-intercept in context of a real-world situation. And that's really all we're going to look at. We're not going to look at data separate from real-world situations. We're always going to look at it couched within a real-world situation. So if you remember this graph from our last video, we talked about the Mathma fish population and how it was, for the most part, decreasing over time. And we looked at different rates, average rates of change. So we calculated it between 2 months. We calculated it amongst the span of maybe 4 or 5 months, that kind of thing. And we could do it, from the very first month to the last month. And we could calculate the average rate of change there. But that might not be, a great representation of, how things are changing each month. Because we've got a lot, in between these 2 months, for example, the slope between those 2 months, or the change between those 2 months, is quite significantly, more than across the whole thing. And so we might want to think about a different way to create a line that best represents this whole, scenario, and the relationship between the amount of months since we started and the population of our fish. So that's where we get to this idea of line of best fit. It's not necessarily the average rate of change, but it is a line that also represents how things are changing with respect to this situation. And so maybe our line of best fit here might be something more along the lines of, something like that, maybe. So we don't know exactly. You could do some math to do it. We're going to use technology today. But maybe our line of best fit is not just the endpoints connected. Maybe it's something else. And so that's what we're going to get into today. All right, so let me throw up a situation here. And this is the population in Iceland in thousands of people. So whereas in the US we talk about millions of people, they're talking about thousands. And so their population is actually really small compared to ours. But here's the population in years since 1970. So the years across the top, the years since 1970 are in the middle here. And that's actually what we're going to use for our independent variable or our x value, in this case t. And then the dependent variable or our y value is going to be the number of people in thousands. And so we're going to take this data and we're going to see if we can figure out what the line of best fit is for this particular data. So number one says calculate the difference between the population successive data points to make a case for why the population growth might be linear. So if you calculate the slope between these two, or the average rate of change, right? We don't know what happens in year 1, 2, 3, or 4, but we know what's happening at 0 and we know what's happening at 5. So we can calculate the average rate of change to kind of get a sense of how things are changing in that time interval. So if you calculate the average rate of change here and between each set of consecutive months, you'll see that it's pretty similar throughout. And so that's a good indication that we're dealing with something that's kind of a linear shape. Because after all, a linear function has a constant rate of change, meaning the rate of change would be the same throughout. Now, this is not a perfect linear function, but you can see that it's pretty close. It says estimate the average rate of change per year. We just did that. Use linear regression to find a linear model for P of T, which is the population of Iceland. So we're going to come up with a linear model that best represents this data. So let me show you the graph of this data first. I'm on Desmos.com. If you go to Desmos, DESMOS.com, and then hit the graphing calculator, you can do this alongside with me. So I've typed in the numbers here. So years since 1970 down the left side here, that's our X value. And then the population, this is in thousands, down the right. And you can see the graph here. Let me kind of bring you up so you can see a little bit better here what I'm typing in and the data points. So you can see the data points. I mean, it's pretty linear. Like you can picture a linear function that kind of goes through those points, right? If you were to draw one, it would be kind of tightly clustered around this line that we were to draw. So that's a good indication that a linear function is going to be a good fit here. There are other function types that we can use. We're going to focus on linear and then maybe possibly exponential later on this year. But let's see if we can come up with a linear function. Let me show you how to do this in Desmos, and then later I'll show you how to do it in your calculator. Okay, so we're going to open up a new line down here, and I'm going to type y1, because if you notice from our table up here, it was y1 and x1, because you can have multiple tables open at one time. So you need to denote which table you're talking about. So I have y, and then just press the number 1, and then you're going to grab this tilde looking symbol here. It's actually at the top left of your keyboard most likely. So you can hit that button there. You might have to hit shift to get it, but the tilde looking symbol there. And then, so that's approximately, because we're not creating a perfect linear function for this data, we're approximating with the line of best fit. So then I'm going to say, okay, m x 1 plus b. So the only ones that need a 1 next to them are the x and the y. Everything else are your values that the Desmos is going to actually create and come up with itself. So a few things to notice here. One is it's created the line for us, the line of best fit. It's drawn that for us, and it looks like it's a pretty good fit of the data. Over here on the left, you can see a few numbers here. We're not going to get into these a whole lot. We'll talk about this R value in our next video. It's called the correlation coefficient. We're going to talk about that next time. But for now, I want you to focus on the parameters. We have m equals 2.80436 approximately. And then b is a little bit over 200. So if we were to take our m and b values and actually create a function for this, it would be y equals 2.8 approximately, so I'm going to approximate it with 2.8, x plus, I'm going to approximate this one as well, 201. So let's think about what both of these mean. Okay, again, this is years since 2070 or 1970. So 201 is probably our prediction, our predicted value for what the population was back in 1970. Now we actually know that the value was a little bit more than that, but that would be our predicted value for the initial or starting point back in 1970. And then 2.8, remember our population is in thousands here. These numbers are in thousands. So 2.8 actually represents going back to our definition of slope that we talked about in the warm-up. So for every increase of 1 in x, we're going to go up 2.8, or 2.8 thousand, okay? Or 2,800 is what that would be, right? So for every increase of 1 in x, well, x is years, right? Years since 1970. So for each additional year, we're going to actually increase our population by 2,800 people. So that's what that means there. For every increase of 1 year, we're going to increase by 2.8 thousand people, or 2,800. So that's how we can interpret that value here. And we can use that to make decisions. Maybe if we live in that country and we make decisions for that country, we can use that to kind of predict what our population is going to be like in future years, and things like that. So that's how we can kind of interpret these values, these parameters in the context of this situation. All right, let's go ahead and move on to our next example, which is Amazon Prime membership. If you study Amazon Prime membership in the U.S., it's actually been increasing quite significantly over the years. But if we look at from 2014 to 2018, I've actually researched what it is in 2020. Again, if you calculate the rate of change here between each 2 points, the slope, so if you subtract, this is an increase of, let's see, 26, I believe. So 26 million here. This one is an increase of 19. This one is an increase of, let's see, 22. The next one is an increase of 10. So it varies a little bit, and so it may not be as good of a fit for a linear function, but we're going to still try to do that with Desmos here. So let's come up with a function for this. So here's the data. As you can see, it's not as good of a maybe a fit to the linear function, because you can see it kind of is curving a little bit here. It's got some curve to it. So linear function is going to be a good fit, but maybe not a perfect fit or even a great fit. And so let's go ahead and do this here. So we're going to type it in, same thing as we did earlier. Y1 tilde looking symbol. A, actually let's use M just to stay consistent here. AX1 plus B. Okay, as you can see, there is some variation here that we're not accounting for with this straight line, right? Especially down here and maybe up here. But overall, it's not a horrible fit, to this data. So let's come up with our function. I'm going to give you the value and see if you can actually write the function and interpret those parameters. So if you can't read it on the screen, M equals 15. We'll use 15.6. We'll estimate it there. And then B equals 27 point, we'll round it up to 8. So take those two values and, can't see it there. Take those two values and see if you come up with a function, and then also interpret those two values in the context of this situation. Okay, so if we write our function here, y equals 15.6, that's mx plus b, it would be 27.8. That would be our function. Okay? 27.8, and by the way, these are in millions. So this is in millions here. So 27.8 million people is our best prediction for the year 2014, which is where we started, or the initial value. Now, is that exactly right? No, but it would be our predicted value. And then 15.6. 15.6 here is our slope. And if we interpret it in the context of the situation, it would be our best predicted increase per year in millions. So for each increase in X, or for every year we go on with Amazon here, they're increasing or at least our predicted amount is 15.6 million per year. Obviously, things are kind of slowing down a little bit. So that may not be the case from 2020 to 2021. But using the data that we have, this is our best prediction for the rate of change per year for this data. And so if we were to predict what would happen in future years, we could do that. So if we want to go out, let's say, and Desmos is really nice in this way. So 2014, if we predict, let's go out 10 years, so to 2024, right here, it's predicting 184 million people are Amazon Prime members in 2024. The U.S. population is a little bit under 330 million. So let's go ahead and see, when would we predict that the Amazon Prime membership reaches the population of the U.S. So if we back out here, let me zoom out, and let's go to 330. 330 would be about in here somewhere. Let's just click on the line and see it. So we're at 322 right now. So 330, and it's probably a little bit under that. about 20 years from 2014. So 2034 is our prediction here. If things kind of follow the same trend here, in 2034, the number of Amazon Prime members will match the US population. Now, we're not guaranteeing that's happened, but using this line of best fit, we are predicting, making that prediction here, using that line. All right, so let me show you how to do this in your calculator, TI-84 calculator. If you take the calculator and hit mode here at the top, I want you to do one step before we get started. You should only have to do this one time. Hit mode, and then go up is the quickest way to get there. To stat diagnostics. That needs to be turned on, and you'll see why later in our next video. But turn stat diagnostics on just by hitting enter there, and then second mode to quit out to the home screen, and then go to stat, which is right here next to the arrows here, and then edit is the first option there. L1 and L2, that's like your X1 and Y1 in Desmos. So you'll type in your X values here and your Y values there. So using this data, we're going to type that in 0, 1, 2, 3, 4, and 6. This is the millions, and then over here we're going to put the millions of Amazon Prime users. So the 18, 44, 63, 85, 95, and 112. Okay, so once you type those in, you quit out again to the home screen, and then go back to stat and over to calc. Under calc, if you scroll down a little bit, you'll see LinReg. That stands for linear regression. And they use AX instead of MX, but it's the same thing. So the A will represent your slope. So if you hit that button there, it's going to ask you a couple questions here. Did you put your X's in L1? Yes. Did you put your Y's in L2? Yes. We don't really need to do anything there. Let's skip the frequency list for now. You won't really use that in this situation. And then store reg equation. So that's going to store the regression equation. We don't really need to do that yet. Maybe in a future course you might need to do that. So really you just go down to the bottom and hit calculate, and it will tell you the A value and the B value. We'll come back to these numbers in our next video. But let's just use the A and the B. If you remember, those were the two values that we saw in the Desmos activity. So that's how you do it using your TI-84 calculator. And you can kind of go back to stat and edit and type in new numbers for a new situation there. All right, let's go ahead and look at our last situation here, which is age on the left, so that's our independent variable, and glucose levels on our right, which is our dependent variable, or our Y value. So I'm going to give you a few minutes to try to come up with a line of best fit for this one, and then we'll do it together. Okay, so we have Y equals, or Y1 approximately equals MX1 plus B. Not that many B's, just one B. Okay, so we have M equals 0.38 and B equals 65.1. So use those two parameters, if you didn't already, to come up with a linear function for this, and then interpret the parameters in the context of the situation. Okay, so if we write our function here, y equals m, we put 0.38x plus 65.1. The 65.1 would be our glucose level if we were 0 years old, which may or may not make sense. But this 0.38, it shows that as we increase in years, so for each year we get older, our glucose level increases by about 0.38 in terms of the units there. And so that's kind of how we can interpret that. So overall, the trend at least is showing that as we get older, our glucose level increases. Now we would need to collect some more data here. I want to point that out. we've only got 1, 2, 3, 4, 5, 6 data points. As we collect more and more data, hopefully the data is going to be kind of tightly clustered around this line so that we can kind of come up with a better fit for the data. But we would need to collect more data to maybe get a better line to represent this situation. And so whether it be Desmos or your calculator, hopefully we've got our goal here of creating linear functions to represent the relationship between two quantities. And then once we do that, we need to interpret those parameters in the context of the situation and tie it back to our definition of y-intercept and of slope.